Thank you all for attending my presentation on deep learning in medical imaging, a practical introduction. My name is Piotr Kram and I'm a computer science student at the University of Cambridge. First of all, I would like to explain what actually deep learning is, because a lot of people don't know the distinction between artificial intelligence, machine learning, and deep learning. Artificial intelligence is a science, like mathematics or biology. It studies ways to build intelligent programs and machines that can creatively solve problems, which has always been considered a human prerogative. Machine learning is a subset of artificial intelligence that provides systems with the ability to automatically learn and improve from experience without being explicitly programmed. In machine learning, there are different algorithms, for example, neural networks, that help to solve problems. Neural network is a structure wherein the artificial neurons make the core computational unit that focuses on uncovering the underlying patterns or connections within a dataset, just like the human brain does while decision-making. Deep learning is a branch of machine learning algorithms that uses neural networks with at least 3 layers. Let me now introduce you to the technicalities of neural networks. To understand what a neural net is, first we need to understand what makes up an individual artificial neuron. Each neuron has a set of inputs. Each input is multiplied with a specific weight that the neuron decides upon. Inside the neuron, we sum up all the weighted inputs and add an offset called bias, which is also specific to the neuron. Such sum is then passed through a nonlinear activation function, resulting in the output of the neuron. The bias and the set of weights that are matched with the inputs are learnable, meaning that the neuron can adapt them based on the feedback it gets about its output. We can understand it as the neuron learning what its parameters should be and what it should calculate. This architecture is modeled on the structure of a biological neuron, which receives input signals through its dendrites and then in the soma decides to fire or not depending on the sum of all of the excitatory and inhibitory signals it receives. Its signal is then propagated through its axons and synapses to other neurons. Another important aspect of a neuron is its activation function. There are many different types of nonlinear activation functions. The nonlinearity not only models the behavior of a biological neuron better, but also allows neural nets to solve problems outside of the very narrow class of linear problems. The most commonly used activation function is the rectified linear unit function, or ReLU, which in its simplest variation outputs 0 if the input is smaller than 0, and is an identity function otherwise. Other commonly used activation functions are the sigmoid function, that is helpful especially in the output layer of a neural net, because it restricts its domain to the interval between 0 and 1. The tanh function, that restricts its domain to the interval between -1 and 1. And the softmax function, which is helpful for the output layer of a neural net solving a multi-class classification problem. Artificial neural network is a machine learning model built using the artificial neurons I introduced earlier. A traditional neural network contains fully connected, dense layers of neurons, where each neuron in nth layer is connected to every neuron in n+1th layer. In other words, output signals of neurons in one layer are inputs to every neuron in the next layer. The output of a neural network is the output of its last layer. It represents a prediction that our net makes for input variables and the problem it's trained for. For example, this neural net tries to predict the price of an apartment based on a set of parameters of the apartment. So the input layer contains the parameters and the last layer contains one neuron outputting a price prediction. The presence of the hidden layer makes this network deep. To be able to assess how well our neural network performs, we need to define a loss function. a metric that will tell us how close the outputs of the last layer are to the truth. Some of the common loss functions include mean-squared error in a regression problem, so for example predicting the price of a house, like in our example, and cross-entropy loss in a classification problem, so for example predicting if an image depicts a dog, a cat, or a rabbit. Now the idea on which the training process is based is very simple. Strengthen the connections that reduce the prediction error and weaken the connections that amplify this error. By modifying a connection between two neurons, one being an input to another, I mean modifying the weight of the input neuron in the second neuron, as well as modifying the bias of the input neuron. We calculate the changes to the parameters using partial differentiation and propagate it from the last to the first layer of a neural network using the chain rule of partial differentiation. You can parameterize the rate of strengthening and weakening of connections and use different algorithms with slightly different properties to update the parameters and optimize the procedure. The process of propagating the changes from the output layer to the input layer is called backpropagation. Now, after we understand what neural nets are, I would like to introduce the notion of a convolutional neural network, which is important to understand when dealing with visual inputs. A convolutional neural network is a class of deep neural networks most commonly applied to analyzing visual imagery. It emerged from connecting the neural net concept with our knowledge about the architecture of the visual cortex. David Hubel and Thorsten Wiesel performed a series of experiments on cats in the 1960s and discovered that many neurons in the visual cortex have a small local receptive field, meaning they react only to visual stimuli located in a limited region of the visual field. The receptive fields of different neurons may overlap, and together they tile the whole visual field. Moreover, the authors showed that some neurons have small receptive fields and react only to images of simple shapes, like horizontal or vertical lines, and that some neurons have larger receptive fields and they react to more complex patterns that are combinations of the lower level patterns. These observations led to the idea that the higher level neurons are based on the outputs of neighboring lower level neurons, contrary to the previous idea of dense layers, where the higher level neurons were based on the outputs of all lower level neurons. In this example, you can notice that each neuron is connected only to a few neurons from the previous layer, not to all of them, like in a dense layer case. This powerful architecture turned out to be able to detect all sorts of complex patterns in any area of the visual field. The most important building block of a convolutional neural network is the convolutional layer. In this talk, I will discuss only two-dimensional convolutional layers, as two-dimensional images are the most common type of medical images. However, the concepts can be analogically applied to a different number of dimensions. Each two-dimensional convolutional layer consists of pairs of learnable filters and biases that transform input images into output images. Filters are three-dimensional matrices of parameters that, convolved with sets of images, amplify some features of the images while repressing others. The depth of a filter is equal to the number of input images. Thus, if we have only one input image, we can have a two-dimensional filter, as in this example. Here you can see small two-dimensional filters that have zeros everywhere apart from on their vertical or horizontal central lines, where the filter matrices contain ones. The output images, also called feature maps, created by these filters, convoluting with the input image, amplify respectively vertical and horizontal lines, while repressing other shapes. Before we discuss in detail how the convolutional layer works, let us define its inputs and outputs. Inputs and outputs of a convolutional layer can be understood as images, feature maps, or as matrices in which each element describes a color of a pixel. For example, a typical input to the first convolutional layer consists of three matrices describing red, green, and blue responses of the input image. So how does the convolutional layer work? In short, it convolves the filters with regions of input images, creating output images. Convolution is just an element-wise multiplication of each two-dimensional slice of a filter with a fixed region in a matching input feature map. After we convolve each filter with each region of input images, we sum up the results per filter and per region, add a filter-specific bias, and save the result in a respective position in an output feature map. Therefore, for each filter we have one output feature map. An optional last step, which is usually performed, is to apply a nonlinear activation function to each element in each of the output feature maps. Here, as an example, you can see a convolutional layer with three input feature maps, two filters, and no activation function applied. Last things that I wanted to mention are the zero padding that we sometimes want to add to input images for the filters to be able to access every element of the input matrix, and the spacing between fragments that are convolved with filters. In this example, you can see the zero padding of 1 and the spacing, also called stride, of 2, in the vertical as well as in the horizontal direction. Changing the stride allows us to tweak the dimensions of the output images. In this example, you can see that using the stride of 2 instead of 1 roughly divided the dimensions of the output images in half compared to the input images. The second very common layer in the convolutional neural nets is a pooling layer. This layer subsamples the input image, typically using the max function, from rectangular receptive fields of pre-specified size, stride, and padding. In this example, you can see a pooling operation of kernel size 2 using the max or the arithmetic mean functions. Other than reducing computations, memory usage, and the number of parameters, a max pooling layer also introduces some level of invariance to small translations. Here we assume that the bright pixels have a lower value than dark pixels, and we consider two images going through a max pooling layer with a 2x2 kernel and stride 2. Image B is the same as image A but shifted by 1 to the right. As you can see, the outputs of the max pooling layers for images A and B are identical. This is what translation invariance means. By inserting a max pooling layer every few layers in a CNN, it's possible to get some level of translation invariance at a larger scale. Moreover, max pooling offers a small amount of rotational invariance and a slight scale invariance. Such invariance, even if it is limited, can be useful in cases where the prediction should not depend on these details, such as in a classification task. So coming back to the convolutional neural network architecture, a typical CNN stacks a few convolutional layers with the ReLU activation function, then a pooling layer, then another few convolutional layers with ReLU, then another pooling layer, and so on. Moreover, we add a few fully connected layers at the end to collate the calculations and put it in the right output format. We train the network using backpropagation, as is the case with traditional neural networks. Now that we discussed the basics of neural networks, I would like to spend some time introducing a few ways of dealing with limited resources, be it a small training dataset or a slow machine. One of the most common problems concerning deep learning in medical imaging, compared to less specialized applications of deep learning, is limited training data. Techniques meant to alleviate this issue and allow deep architectures to learn fast and generalize well are transfer learning and off-the-shelf features. In the transfer learning approach, the network is first trained using a different, usually much larger dataset. Then the network is fine-tuned through additional training with data specific to the problem to be addressed. The idea behind this approach is that solving different visual tasks shares a certain level of processing, such as recognition of edges or simple shapes. Another approach that addresses the issue of limited training data is the deep off-the-shelf features approach, which is similar to transfer learning and is sometimes considered a part of transfer learning, with the difference being that the last layers of a CNN are replaced by traditional classifiers, such as support vector machines or decision trees, and the early layers are not additionally trained. This way we can use already trained models found on the internet to solve the issue of a small training dataset or a low computational power, because the network will usually train much faster if we use transfer learning. Data augmentation is another approach we can use to battle the problem of a small training dataset. Data augmentation artificially increases the size of the training set by generating many realistic variations of each training instance. For example, you can slightly shift, rotate, resize and flip every picture in the training set by various amounts and add the resulting pictures to the training set. This forces the model to be more tolerant to variations in the position, orientation, and the size of the objects in the pictures. For a model that's more tolerant of different lighting conditions, you can similarly generate many images with various contrasts, as you can see in this example. Although data augmentation works great with most of the problems, there are problems where it's not so useful. For example, for a dataset of X-ray images in which images are positioned in the same way and created so that different types of variations between pictures are minimized. Following this technical introduction, let's now talk briefly about current state-of-the-art deep learning approaches used in medical imaging. The majority of deep learning applications in medical imaging can be divided into three categories: classification, segmentation, and detection. I will briefly discuss each of these categories and their corresponding deep learning architectures. In a classification task, an object is assigned to one of predefined classes. A number of different classification tasks can be found in the world of medical imaging, such as classifications of an image to determine the presence or an absence of an abnormality, classification of abnormalities as benign or malignant, prognostication. The current state-of-the-art deep learning architectures tackling the classification problems are various types of convolutional neural nets. The one I would like to discuss is a residual network, or in short, a ResNet. This architecture won the ImageNet Large-Scale Visual Recognition Challenge in 2015, arguably the most prestigious visual deep learning challenge in the world, and thanks to its simplicity, gained widespread popularity. Multiple versions and implementations of the ResNet architecture are now publicly available on the internet. The original ResNet version is an extremely deep CNN composed of 152 layers. Such deep networks are very hard to train, but the trick that allowed this architecture to learn was to use skip connections. It not only allows deep layers of the network to get feedback on their performance fast, but also makes the function that the network tries to model easier to learn by subtracting from it the identity function. The other practice used in the ResNet architectures that makes the training process faster and more stable is batch normalization, which recenters and rescales intermediate outputs. In deep networks, it's usually applied every few layers. Here you can see a visualization of the skip connection and a visualization of the ResNet architecture. You can notice that the core of the ResNet architecture consists of multiple repeatable blocks of two convolutional layers with batch normalization and a skip connection. Such a block is also called a residual block or a residual unit. Other than that, ResNets only use variations of convolutional pooling and fully connected layers, which I introduced earlier. Second common category of deep learning problems in medical imaging is segmentation. In an image segmentation task, an image is divided into different regions in order to separate distinct parts or objects like organs, substructures, or lesions. Segmentation is often used as preprocessing step for feature extraction and classification. The simplest approach still used today is to classify a pixel based on surrounding pixels. Unfortunately, this method ignores wide context of segments and is inefficient because we process same pixels multiple times. A deep learning approach that works well for this kind of problems is a fully convolutional neural network. The difference between a classical convolutional neural network and a fully convolutional neural network is that the latter doesn't have a fully connected layer, so its output layer is a convolutional layer. It also often uses an upsampling layer, or in other words, a transposed convolutional layer, so that the outputs of the network are of the same size or similar size as the inputs. You can understand an upsampling layer as a pooling layer with a fractional stride that is smaller than 1. Here you can see an example of an upsampling layer of stride 1/2. Another advantage of a fully convolutional neural network is that it can be trained on images of variable size, because the number of parameters for convolutional layers doesn't change if dimensions of input images change, contrary to fully connected layers. The specific architecture that proved to work well that I would like to talk about is U-Net. The U-Net architecture contains two paths. First path is the contraction path, also called the encoder, which is used to capture the context in the image. The encoder is just a traditional stack of convolutional and max pooling layers. The second path is the symmetric expanding path, also called the decoder, which is used to enable precise localization using skip connections and transposed convolutions. The last common category of deep learning problems in medical imaging is detection. Detection is a task of localizing and pointing out an object in an image. In the world of medical imaging, detection is often an important step in the diagnostic process, which identifies an abnormality, an anatomical structure, or a region of interest for further classification or segmentation. A simple approach to this problem is to have two kinds of networks. One that proposes the interesting regions, for example by outputting bounding box coordinates, and the other one that classifies the bounding boxes. A better, more end-to-end approach is to use a single neural net like the You Only Look Once net, or in short the YOLO net, one of the current state-of-the-art architectures for detection. YOLO's third version that appeared in 2018 is a very fast and accurate object detection architecture. It's a fully convolutional neural network that detects objects at 3 different scales. It's built from stacking up convolutional layers, residual blocks, and upsampling layers. We already talked about all 3 of these structures, so I won't dwell upon it. Some of the tricks used in the YOLO third version network are default bounding box sizes, chosen by looking at the most common bounding boxes in the training set, logarithmic bounding box coordinates, and separate detection layers for large, medium, and small objects, respectively at 82nd, 94th, and 106th layer. Now I would like to walk you through a simple, practical example of detecting pneumonia from X-ray images using the transfer learning approach on a version of the ResNet architecture containing 50 layers. For the demonstration, I'm using a notebook which I created on the Kaggle platform, which is a great educational platform for data science enthusiasts with 3 legal datasets, data science competitions, and lots of open source deep learning solutions provided by the public. At first, I imported required libraries. Then I checked that our training set contains 5,218 images, including 1,342 images of healthy patients and 3,876 images of patients with pneumonia. This training set is actually large enough for building a deep learning architecture from scratch, but you won't always be so lucky in real life, thus I focused on a transfer learning approach. With transfer learning, sometimes you can train a classifier with as little as 10 or 20 examples per class. Here you can see a small visualization of 5 samples from each of the training classes. In this section, I define, compile, and train the model. Here you can see that I'm using the ResNet 50 model implementation provided by TensorFlow. The include top parameter indicates if I want to import the last output layer of the model. With transfer learning, we don't want the last layer as we want to train our own output layer. The weights parameter equal to ImageNet specifies that I want to use the weights that have already been pre-trained on the ImageNet dataset. The pooling argument equal to AVG or max specifies that the second but last convolutional layer of the model should be squashed into 2 dimensions using one of these 2 functions. At the end, I'm adding a dense layer with one output neuron with the sigmoid activation function that restricts the output to stay between 0 and 1. This way I will teach the network to predict 0 for images of healthy patients and 1 for images of ill patients. Next, I'm freezing the ResNet part of the model. By freezing, I mean that I'm not training the weights of the residual net, focusing only on my output dense layer. Later, I'm compiling the model using a suitable optimizer, a loss function that penalizes bad predictions, and a metric that the network will report to me during training and prediction. Next, I create generators of image data that will fetch the training, validation, and test images for me. Then I assign class weights to the classes counteracting the effects of having many more images of patients with pneumonia than images of healthy patients. Next, I compile the model using the function I introduced before and train it using the generators of images. After training, I'm saving the weights of the model to a file. In the last section, I'm testing the model on a dataset of 624 images that the network hasn't seen before. You can see that with a few seconds of training, I got a stunning accuracy of around 85% on detecting pneumonia from X-ray images. This concludes my short presentation about deep learning in medical imaging. If you have any questions regarding the presentation, please email me on pk485@cam.ac.uk. Thank you for your attention.